So last time we introduced this idea of energy and work, and now we're going to begin to define specific types of energy and give a definition mathematically of work. And we're going to do this for one specific object. So that's going to be our system. In order for this to make sense, we're going to have to understand what all the different available types of energy are. So let's remember what kinds of energy we might have in a system. So we could have kinetic, we could have gravitational potential energy, we could have spring potential energy, we could have chemical potential energy, we could have thermal energy. In fact, we could have a bunch of different kinds of energy, and you might not even know all the different kinds of energy that could be available to the system. But it turns out you don't have to know all the different kinds of energy. What really matters is how the energy is changing in the system. So when you go through this, what that means is you're going to have a delta in front of each one of these terms. So you're going to have a delta K and a delta UG and a delta U spring and a delta E chem and a delta E therm and so on and so forth. And that's going to be equal to work. And like we said last time, technically there's a heat here as well. It's just we are not dealing with that in this unit. So, the reason why it doesn't matter that we don't know what all these other terms are is because they might not be changing. For example, nuclear energy is one of these terms out here, the energy bound in the nucleus of these atoms. But that's not going to be changing. So it's going to disappear from this term down here. The thermal energy is only going to change if the temperature of the objects is changing. There's another way also in our book in particular, thermal energy changes if there could change anyway if there's friction in the system. So we're not going to deal with that for a while, so that's often not going to be changing. Chemical energy is only going to be changing if there are chemical bonds breaking or forming in the system. We're not going to be dealing with that. Spring energy, predictably, is only going to be changing if springs are stretching or compressing. We will not be dealing with that for at least a while. We're going to go ahead and set that equal to 0. The ones we are mostly going to be dealing with in this section right now are kinetic energy, gravitational potential energy, and work. Gravitational potential energy you have to keep if an object is changing height. And kinetic energy you need to keep if an object is changing speed. So we can look at the definitions of these different terms and use them to actually calculate something. So let's start building this equation one piece at a time until we're ready to calculate something. So let's start with kinetic energy. It's right here. The mathematical definition is 1/2 times the mass of the object times its speed squared. You can see that this will always be a positive value or 0 because the speed is squared, so that will always come out positive or 0. The mass is already always positive, or maybe 0, but usually positive. And then we have a 1/2. So this is always a positive term unless it's equal to 0. We can also define its change. Since that's a difference, this could end up being negative as well as positive. And we can easily calculate these numbers. So, for example, this jet that's more like a drone, I guess, except it's going very fast. So it's 1/2 mv squared, 1/2 times its mass, 1,200 kilograms, times 450 meters per second. We're going to pretend that is 3 sig figs, because that's what I prefer, and I don't always manage to get it in the notes. So that's 1/2 times 1200 times 450, square that. So 122 times 10 to the 8. And let's look at what these units are. We have a kilogram times a meters squared over seconds squared. If you remember, a newton is equal to a kilogram times a meter per second squared. So this, a kilogram times a meter per second squared times a meter, is a newton times a meter. And we have a name for this unit. This is called a joule. And we give it the letter J. Now, you should not confuse this with the J that we have for impulse, and there's 2 reasons for that. One, this is a unit, right? So it always comes after a number. And 2, J as impulse is a vector quantity, right? Whereas this, first of all, kinetic energy is not a vector, right? It's a scalar number. I guess I haven't said specifically that energy is a scalar, but you haven't seen any vector symbols. It has no direction. It's just an amount of something. And so there's no vectors anywhere. This is just an amount of stuff. This is a pretty large amount of stuff. 1.22 times 10 to the 8 joules is the amount of energy there. We also want to calculate the change in kinetic energy for this car. So we start at Ki is equal to 500 kilograms times 20.1 meters per second squared. And so we get 500 over 2 times 20.1 squared. And so that is 1.01 times 10 to the 5 joules. And then Kf is equal to 1/2 times 500 kilograms times 13.4 meters per second squared. And that is equal to 4.49 times 10 to the 4 joules. Just make a little separator here so we can get the final value. So delta K is equal to Kf minus Ki. And so that is going to be equal to our 4.49 minus our 1.01 10 to the 5. And so we see that there's a net loss of 5.4. I can't read. But that number, joules. Negative 5.61 times 10 to the 4 joules. And it's fine that this number is negative because that is how much the kinetic energy is changing. It's dropping by that amount. You started with a high amount and you've ended with a lower amount. So why does kinetic energy change? Well, it can change for a number of reasons. Something can take that energy away from you, from outside the system, and it would normally do that with, well, it has to do that with either work or heat. Heat, I've mentioned, is going to be in a different section, different unit, usually a different semester. So this is going to be doing it through work. So work is a transfer of energy into or out of the system by a force. And there's an equation for it. The work is equal to a magnitude of force. Notice there's no vector symbol here. So this is a magnitude times a magnitude of displacement. So this essentially is a distance. So we have magnitude of force times a distance times the cosine of the angle between the force and the distance. So for example, in that car scenario, you had to apply the brakes, right? So you were slowing down, actually, this turns out not to be a great example. Let's say you had locked brakes. That will work as a better example. If you had locked brakes, now there's a static friction force of the road backwards on you. And you could think of this as a backward force while you are continuing to move forward. So the angle between those two is 180 degrees. Okay? And so in that case, work would be the magnitude, so work would be the magnitude of Fs times the amount of distance you went times the cosine of 180 degrees, which if you remember your unit circle, cosine of 180 degrees is -1. So since these are both magnitudes, they have to both be positive. This work is going to be negative. It's going to take energy away from the car, which is what we expect. Okay, so what can we do with this? Let's say that we have a little cart, and the cart has a fan on it. And because of the fan, the air in the room will cause a thrust force on the cart. So that thrust force is causing a 2.00, I don't know why I insist on 3 sig figs, but I want it, Newton force. And in our first example here, we're going to go 10 centimeters. Okay. So I say the cart is initially still, so it's very easy to calculate the initial kinetic energy. It's 0 joules. And I want to find the cart's final kinetic energy. Okay. So the equation that I'm going to use is delta E is equal to work. And then for the delta E, I'm going to think about all the possible energies that could happen, right? Well, we've already talked about how these are probably not applying. So is the cart changing height if it's just rolling across the table? No. Is the cart changing speed if the fan is pushing it forward? Yes. So we need a delta K. We don't need a delta UG or any of these others. So we're going to have, for our equation, delta K is equal to W. Some books call this the work kinetic energy theorem. I think that is kind of a overstatement. It's a sort of grandiose term from an equation that comes out of a more important equation. I wouldn't jump straight there unless you're pretty confident as to why. I would start with this equation. This equation, more grandly and more appropriately, is the first law of thermodynamics. Okay, so we have Kf minus Ki is going to be equal to the work. We know Ki is 0. So all we have to do to find Kf is to calculate the work. All we have to do to find Kf is to calculate the work. So that's going to be equal to the force times the distance it goes times the cosine of theta. Well, we know the magnitude of the work. We know the distance that goes. So the question is, what is the angle between the direction of the force and the direction the cart goes? the cart is going forward. The force of the air on the fan is also pointing forward. Don't confuse this with the direction that the wind is going from the fan, right? The fan is pushing the air backwards, which means by Newton's third law, the air is pushing the fan and the cart forward. So, if they're both pushing, if the force is forward and the cart is moving forward, then what's the angle between two vectors that are both pointing forward? That angle is 0 degrees. So Kf is going to be equal to 2.00 newtons times 0.1 meters times what's cosine of 0? It's just 1. So that's 0.200 joules. Okay. Now we're going to do a slightly different problem. We have our cart. It's rolling. This time the fan is pointing backwards. So the force is going that way while the cart is still going this way. So think of this as kind of a braking action, right? So the cart was already going forward, but the fan is blowing so that it's pushing the air this way, which means the air is pushing the cart back that way, and it's causing the cart to slow down. But it's kind of gentle, right? It's just a fan. It's not going to slam the brakes. And so we want to figure out what the cart's kinetic energy is after it goes whatever distance. 5. Remember, I want 3 sig figs, so it's going to be 5.0. That's 60.0 and so forth. Okay, and we want to know the cart's final kinetic energy. And I'm going to tack on another question after that. Similar scenario, we're going to have delta K is equal to W. So we're going to have Kf minus Ki is equal to W. So Kf is equal to W plus Ki. Now the difference here is we actually have a Ki. So for Kf, we're going to have two equations. We're going to have our FD cosine theta, but we're also going to have 1/2 mvi squared. So let's do these each. For our F, we have a 1 Newton. For our D, we have 5 centimeters. Now let's think about the angle this time. We are traveling to the right, but the force is pushing the cart to the left. So what's the angle between pointing to the right and pointing to the left? That's 180 degrees. So we have a cosine of 180 degrees. And then we have 1/2 times the mass, which is 500 grams, 500 grams times 0.6 meters per second squared. Okay, let's calculate that all together. So we have 0.5 times 0.5 times 0.6 squared, and then we're going to add to that, we're going to subtract 0.05 for this, and so we're going to have 0.04 joules. Okay. Now what we want to do, this wasn't originally written on the question, is what is the final speed? So 1/2 mvf squared is equal to kf. We have kf, so vf is equal to 2kf over m, and then take the square root. So that's 2 times 0.4 joules over 0.05 kilograms. 0.5, not 0.5. So we have 6.04 square root. Answer 0.40 meters per second. And if we compare that to our original answer, it was going 60 centimeters per second. Now it's only going 40 meters per second. So it seems to line up.